So our real numbers is what we're looking at the moment. So today we're going to talk about how we represent these things. And as I mentioned yesterday, all real numbers can be placed on our real number line. So that's the first thing. But that can be described, well, geometrically. So using the picture of the line. Yeah, how sometimes you solve inequalities and it says, oh, place your solutions on a number line. So that's a geometrical way of doing it. Algebraically is probably the most common way we do it, where we're using equations or equations. There's other ways. There's a thing called interval notation. Now this notation is often used when we're talking about functions and we want to know what's called the domain and range of functions. And set notation is yet another way. It's a more formal way of describing every possible solution, every possible number. Okay, so types of intervals. We can have what's called a bounded interval, and that means that the interval of numbers we're talking about has two distinct endpoints. So that's bounded. It has a start, it has a finish. And then you can have unbounded, where, well, it's only got one endpoint. The other one keeps going to infinity, or negative infinity, depending on the direction. And then we could have closed, so whether or not the endpoints are included or not. So closed, they're included. And open means, well, there's an endpoint that's not included. And then we have a degenerate. And a degenerate is just a single point, a single number. Okay. So x is greater than 5. If we had this particular answer to our problem, then graphically we would draw it something like that. So it's not equal to, so we have an open circle. So the open circle indicates not included, and then the arrow points in the correct direction. Now I always place the arrow slightly above the line. Some people put it on the line itself. The reason I don't do that is because I find, depending on the colour of pen I'm using, you can lose the solution in the number line itself. So I always put it slightly above the line. That would be open, unbounded. So open and unbounded. In interval notation, that's how we would represent it. When it's not included, then we put a parenthesis. So that indicates that the endpoint's not included. Now when infinity is an endpoint, it's always not included because, well, theoretically you can't reach infinity because it just keeps going and keeps going, so you never get there. And in set notation, it's simply something like this. So the braces is what we use to indicate this is a set of numbers, and I'm saying x, the colon means such that, and then we basically have got the inequality down there. So we're saying x such that x is bigger than 5. Okay, so what about if it's included as well, so less than or equal to 6? The only difference here really is we colour in the endpoint, so it becomes solid. So that tells us, yeah, this is part of the solution. So that's a closed unbounded interval. Closed unbounded interval. Now when it's closed, we use the square bracket rather than the parenthesis. Okay. In between 2 points, and this time both endpoints are not included, so that's open but it's bounded. It's a bounded interval. And that's how we would have it in both interval and set notation. Well, this one, they're included now. So that's a closed bounded interval. And would look like that in our different notations. One is included, one's not included. We have something like that. What on earth do we call it? Well, is it open? Is it closed? Well, one end's open, one end's closed. So I just, look, it's a bounded interval. This is bounded. I can't really say if it's open or closed because one is, one isn't. And I would write it like that. All right, so our rational numbers. Rational numbers, they are the ones that can be written as fractions basically, but there's our formal definition. It can be written in the form a over b, where a and b are integers. Irrational numbers then are all the other ones. So they're all the numbers that are not rational. Now, every single irrational number will become an infinite decimal. Now, yesterday we talked about terminating decimals and recurring decimals. Okay? So they are rational numbers. The terminating ones are always rational. The recurring ones are always rational because we could end up writing them as a fraction. But all these ones that just go on forever and there is no pattern to it, they are our irrational numbers. And basically we can't work them out exactly because there's no pattern to it. then we can never actually say exactly what the number is, because it just keeps going and keeps going. So we don't know the value. We're going to prove that the square root of 2 is indeed an irrational number. And the technique we tend to use for proving something's irrational is what's called proof by contradiction. So you want to contradict yourself in your proof. So we assume the opposite. I'm going to assume the square root of 2 is indeed a rational number. Now, if that's the case, I can write it as a fraction. A over b. What are my conditions on a and b? Well, they're going to be integers that have no common factors. Another way of saying that is co-prime. Some people write that because it's less words to write. We can say, oh, well, where a and b are co-prime. Well, playing around with that, I get b times the square root of 2 is a. If I square both sides, 2b squared is now a squared. So that tells me a squared is divisible by 2, because it has a factor of 2. Now the thing with squares is your factors always happen in pairs, because a square is a number multiplied by itself. So if I have 2 as a factor, I must also have another factor of 2. In other words, 4 must be a factor as well. So as prime factors of squares appear in pairs, any square that's divisible by 2 is also divisible by 4. So therefore I now know a squared is divisible by 4. So I could say 2b squared is equal to 4 times some integer, some number. So b squared is 2k. Well, that's now telling me b squared has a factor of 2. So both a squared and b squared are divisible by 2 and have a common factor. Well, hang on. We said a and b are integers with no common factor, so how on earth do their squares all of a sudden have a common factor? That's impossible. So a and b, no common, there's your contradiction. In the very first line I said they have no common factors, but now by using that fact, I've come up with the conclusion that they have a common factor. I'm contradicting myself. Therefore, my original assumption must be incorrect. So the square root of 2 can't be rational. Therefore, it's irrational by contradiction. Significant figures. So just a quick word on significant figures. See, our irrational numbers, we can't work them out exactly as I say. So very often we use approximations if we want to use them in the real world for a calculation or something. So when we are approximating, we tend to either round to decimal places. That happens a lot. But of course in science, we tend to go with significant figures because we could be dealing with a very, very small number. And so you don't want to say, I'll round off to 23 decimal places or something like that. We tend to use scientific notation or standard notation and then use significant figures. So how do you round off significant figures? I mean, rounding off decimal places, I think we know how to do that. That's nice and easy. But what about significant figures? Okay. Basically, it is the same, but what we do is we start at the first non-zero digit and count to the required number, and then round. So if a question said, look, write correct to the given number of significant figures. So what would 0.050703 be to 2 significant figures? So we start at the first non-zero number, which is 5, and we count 2 figures. So 50, round. Oh well, next number is 7, so I round up. So it's 0.051. If it was 3, same deal, I'll start at the 5. 507, next number's a 0, so I leave it at 7, 507. If it was 4, 5070, next number's a 3, so I leave it down. Now the thing with significant figures is, unlike decimal places, is I do write that 0 down. The word significant is important. Why do we write it down? Because we're saying, hey, this number is significant. Because it's telling us how accurate we can measure it. Now, if I didn't put the 0 there, it would imply that I could only measure this to a degree of accuracy of 4 decimal places. But by having the 0 there, it was telling, no, you can measure this to the degree of 5 decimal places. It just happened that when you measured it, it landed exactly on the boundary, and so that 5th significant figure was 0. So by putting the 0 there, you're telling them, this is how accurate I can measure this thing. Whole numbers are far more interesting though. 3,000 to 2 significant figures. You start at the first non-zero number, which is 3. Count 2, so that's 0, round. 0, we leave it. So it's actually 3,000. 3 significant figures. I start at the 3, count 3, next number 0. It's 3,000. 4 significant figures. Oh, well, I'll count it's 3,000. They all have the same answer. Because in this case, some of these zeros are not significant. What they're doing is they're holding place value. Because if you didn't write those zeros down, so take the first one. If I just wrote the 2 significant figures down, I wouldn't have 3,000, I'd have 30. And to say 3,000 is the same as 30, of course, is ridiculous. So they're performing a different role. This is why we use scientific notation, because if we put it in that form, we can drop off those not significant zeros. So if it is ambiguous, like these last 3, that's when we use scientific notation, if we're trying to demonstrate how significant the answer is. So the first one, and now look, they all become different answers. So how do we work out how many significant figures? Because that's important. We want to know how significant is this answer. Start at the first non-zero digit and simply count until you get to the end of the number. Right? Count till you get to the end of the number. So back to our 0.050703. I start at 5 and I count. Oh, there's 5 numbers there. It's got 5 significant figures. 0.010031. Start at the 1, count. It's also got 5 significant figures. This one here, 0.0100310. Start at the first one, count. That last 0 must be significant. Another way of thinking about it is, if you get rid of the 0, does it change the number? And if I get rid of that 0, it doesn't change the value of the number. So it must be significant. Why put it there? 6 significant figures. Whole numbers. Still follow the rule, I reckon. You start at the 1, I'm going to say 4. But yeah, it could be 2, could be 3, could be 4. So what would I put down? I'd put down 4. And you know why I'd put down 4? I might not be right, but I can't be wrong. With the information they've given me, I can't be wrong. Now, they might give me more information. They might tell me something about what they did in the experiment or something like that, which would allow me to work out which one it is. But if they don't give me that information, then any one of those 3 answers could be right. So I always go for the biggest one. If it is ambiguous, use the biggest one. Okay, that'll do us for today.